Welcome to the Chem Doctor, and this presentation is going to be the first in a series that teaches the viewer about reaction mechanisms and elementary steps. Now, what you're looking at here is an overall balanced chemical equation for the formation of NO and CO2 from NO2 and carbon monoxide. The chemical kinetics for this overall balanced chemical reaction has already been analyzed, and we've determined an experimental rate law that's shown over here on the right side of the screen. Now, I have to assume in this presentation that you have already done the first part of a chemical kinetic sequence, and you understand at this point how an experimental rate law is determined. So it will have either been done by two methods, either using initial time kinetics, where you use the ratio method to determine the value of x, or the reaction order, that would be this exponent here, or the integrated rate laws were used, where time versus concentration data was analyzed by three graphical methods, where the data was graphed for a zero order reaction, for a first order reaction, and for a second order reaction. And when you look at the data fits, whichever data fit gave you a linear representation of that data, so a straight line, that provided the order of the reaction. So all of that work has been done for this chemical reaction, and the experimental rate law was determined for it, and that rate law says that the rate of this particular reaction will be equal to the rate constant times the square of the concentration of nitrogen dioxide gas. Now, note that carbon monoxide is actually not shown in this expression, which means that the order of the reaction for the carbon monoxide is zero order, and that's why it doesn't appear in the rate law. Now, at the point where a chemical kineticist has this kind of information, where they have analyzed the kinetics for a chemical reaction, they've determined what the rate law is, what they normally do next is to try and come up with an understanding for exactly how this chemical reaction happens in terms of its pathway. And what I mean by pathway is that if you imagine that you're going to climb a mountain, all right, you can imagine that there's at least a couple different ways to go up this mountain. You can imagine that one way might be this way here, where we just go straight up this face to the top. All right, and you can imagine another way, maybe a second way, that instead of going straight up the face, it's going to go around like this in a spiral. So you maybe take the easier route, but you can see that if you take the easier route, that it's going to take a lot longer, because the distance that the climber would take to get up here is going to be also a lot longer. So the time frame involved in either pathway 1 or pathway 2 is going to be distinctly different. So the chemist is going to look at this chemical reaction and see if they can come up with some idea about a pathway, and this is going to lead to what we call a reaction mechanism. And the reaction mechanism is going to be a series of steps. Now, these steps are completely hypothetical in nature. In other words, you're actually looking at what would be considered a proposal or a hypothesis. And what that means is that this is a situation that essentially is unknown. What the chemist is going to have to do later is go back in and set up a series of chemical experiments in order to either prove or disprove this hypothesis. But for now, what we're going to end up with is what we call a series of elementary steps. And these steps, by analogy, are like the pathways chosen to climb the mountain. All right, so for this chemical reaction, we might propose these two steps. Now, the beginning student of chemistry needs to be assured that I at least know of no circumstances where beginning students are actually asked to propose these themselves. But what's going to happen is the teacher or the professor is going to offer up steps like these, and then they're going to ask you to either validate them or invalidate them. And what I want to talk about here initially is how we make, or how we understand how they set these steps up. Now, what they're going to do is give you, like I said, a series of elementary steps, and for this particular mechanism, there are two of them. So we visualize the first step being a reaction between two NO2 molecules to produce NO3 and NO, and then a second step where the carbon monoxide comes in, reacts with the NO3 and produces NO2 and CO2. Note that I've also stipulated over here on the right that one step is slow and one step is fast. Now, before we get into the nitty-gritty on how we evaluate these two steps, what I want to do in this presentation is deal with the issue of the slow and the fast, the idea that one step is slow and one step is fast. To do that, we need to look at an energy diagram that represents the two elementary steps of this reaction mechanism. So I'm going to do that right here, and this is going to be a standard reaction diagram. You should have seen these kinds of diagrams before, where we have energy on the vertical axis and we have the reaction progress on the horizontal. And for this series of steps, we're going to assume that the overall reaction is exothermic. Normally, probably in the past, when a teacher or a professor showed you a diagram like this, there was one peak in the middle that led, or that blocked, the progress between the reactants and the products. Now, in this elementary situation where we have two steps, and we're stipulating that the first step is slow and that the second step is fast, our diagram is actually going to have two steps in it, or two peaks in it. So the first peak is going to look like this, and then there's going to be a second peak which is lower, and then our progress is going to sweep down like this, and we'll have our platform for the products. To keep things simple, I'm just going to call the first platform R for reactants, and the second platform lower, I'm going to call this P for products. And then I'm going to go ahead and extend this line across like that so we can talk about the energy differences here. Remember that this gap in here, the difference in energy between the reactants and the products, is the delta H of the reaction. And that's not the subject of this work, but I want to remind you that when you look at a diagram like this, that you're getting really two kinds of information out of it. You're getting the difference in potential energy between the reactants and the products, which has nothing to do with essentially the kinetics of the reaction. And then second to that, we also gain information about the kinetics, and that data is shown here. So you can see for the first reaction that we have this peak, which correlates to this energy here, which represents the activation energy, which we're going to call E sub A1, because this is the energy of activation for the first step. So I'm going to put that in here to be really clear about it. This is E sub A1. And then you see we have the smaller peak, which is going to correlate from the bottom of this well that I've indicated here. Okay, and I'm going to brighten this up. You need to be able to see this arrow. But this peak is this gap, very small gap, that occurs between this point and the top of this peak. And the top of this peak is E sub A2, or the energy of activation 2. And you can see that this gap is much smaller than E sub A1. So this is E sub A2. Now, when you look at my graph, you can clearly see that the distance that that is that correlates with E sub A1 is a much bigger distance than E sub A2. So we can write this inequality like this. So E sub A1 is a much bigger value than E sub A2. That means that the amount of energy that the reactants are going to have to get to the top of this peak is going to be much greater than the energy that the reactants are going to have once they're up here and are proceeding towards the second step of this reaction. So this being reaction number 1, this being reaction number 2. All right, and so let's talk about what this means when we say that reaction or the elementary step number 1 is slow by comparison to the elementary step number 2. If you think about the reactants being in a foot race, so I'm going to draw a picture of a person here who's running. All right, and the person's running in this direction, and they're starting the reaction. So at first they're on the flats, and then all of a sudden we have this huge hill that they have to go over, and then below that is a second hill. You can see that once the individual has reached the top of this hill here, which is going to take them, they're going to have to think of the energy they're going to have to expend to get up this hill. All right, and once they get to the top of this hill, it's going to be absolutely nothing once they get down to this point in order to have to succeed in crossing over this hillside here. In other words, this is going to be relatively easy to thunder over the top of this hill by comparison to the first one. So the first hill is going to require a lot more energy to get to the top of, and it's going to take a lot more time. So we would say, in order to get over the first hill here, and I'm going to go ahead and call this E sub A1, that this is going to be rate limiting. All right, it's rate limiting because it's going to take you more time to get over the top of this first hill than it will the second one. So the second hillside is going to require less time to circumvent it or to get over the top of it than it does to get over the top of the first hill. So we say the first hill is rate limiting, and this is going to determine literally the rate of this reaction. All right, and so in terms of the elementary steps, it's going to be important for you to determine, in terms of being able to make a decision about the validity of this mechanism, you're going to have to know which step is going to be the slow step relative to the other steps that are proposed in the mechanism. And for the most part, when your teacher or professor offers you a series of these steps, when the first step is the slow one, this series of propositions is going to be easier to determine their validity when the first step is slow relative to the second. And with that, what I want to do is go ahead and close the video. In the next video, what we're going to do is explore the actual process you have to go to evaluate these two steps to determine their validity. So I'd like to thank the viewer for watching, and you can see more videos at www.chemdoctor.org.